Gosh, Mom, tag me in. Hey, welcome to Vibes Lab. We're looking at cantilever beams this lab, which are essentially beams that are fixed completely on one end. So we've kind of simulated some of those environments here. First part of the lab, you're going to use one of these mechanical wave drivers once again. With one of these signal generators, you can tune it to a certain frequency and amplitude, and you're going to look experimentally for the different resonance modes and where they occur in the frequency range, and that's where the amplitude is the highest. For each of these different beams of different lengths. So this one is looking at beams of different lengths and the relationship to resonance, frequency. You can use this strobe light to try to get close, but not exactly on the frequency on here. And the aliasing will allow you to see what the motion is much more clearly. I'm not going to do that right now because I'm going to flash our friendly cameraman over here. In the second part of the lab, you're going to come over here and you're basically going to clamp different materials. You're going to clamp different materials to the brass or the different beam materials that you have. And you're going to put an accelerometer on different ones of them. And you're going to, there's a bunch of beams down here to try some different ones. And one thing that's important is where the accelerometer goes on your beam is really important, because if you put it here, you're going to actually affect the vibration. What's going to go on here is we're going to clamp some cantilever beams and look at a bunch of different beams with different properties. So down here we have some of brass, we have some aluminum, some steel, some plastics, and you're going to put your accelerometer on here and use a fast Fourier transform in LabVIEW to get the different resonance modes and the frequencies. Now the question is where do we want to put this. If you put it on the end, it's actually going to affect your vibration quite a bit because you have a mass here. It's no longer just a cantilever beam. If we put it here, it'll affect it less, but the measurement might be a little bit worse. So this is kind of the lesser of the... Manny, what are you doing? Manny? This is kind of the lesser of the two evils, just to put it here. So we're going to make sure that this follows through to your dual mode amplifier, and that's going to scale our voltage for us from G's. And then we're going to also turn on our data acquisition box back here, and that's going to feed to the LabVIEW. And then what we're going to do is calculate the frequencies experimentally, and then compare that to literature values for our Young's modulus, and see if we're in the range of acceptable values for our different beams. So once you have your experimental values for the first part, which is comparing cantilever beams of different lengths, and the second part, which is comparing cantilever beams of different materials, we're going to look at how we can validate that with theory and see how far off we are from the real cantilever beam behavior. So here you see it's fixed on one end. There's this equation where we can calculate the natural frequency of different modes. So here are the first couple modes of vibration, and you can see we can predict the natural frequency based on the Young's modulus, the inertia, the mass, and the length. And these different coefficients that change based on each of the modes have been calculated experimentally. So your goal is, for the second part of the lab, is to try to find these first three modes using spectral measurements, an FFT, in LabVIEW. So once we have these three modes, these resonance values, experimentally from a fast Fourier transform, you're going to also measure the mass of your beam, the length of your beam from your clamped part, and then also the inertia, and you're going to backsolve for the Young's moduli and compare that to literature values that you have to find online. The other thing that's going to happen is, for the first part, you're going to take your lengths, and what you'll notice is that none of these values are being varied, so except for the length. So the goal of this is going to be to plot your natural frequency against the length for the first mode and for the second mode, and see what type of behavior you have, and does it make sense. So when you get that plot of natural frequency against length, what's its behavior, what's its curve look like, what's its parent function, and if you curve fit it for the parent function that it should have, you should get a low % error. So that's one way to quantify the error. Or you can manually calculate what your natural frequency should be based on these if you measure them for the first part setup and predict them and get a % error that way. Another thing that is also important is to calculate what this coefficient should be between the two resonance modes. So what's the relationship from one mode to the other if you were to divide these equations, and you can get the relationship that way. So that's kind of the goal of the first part. And the second part, one other quick note is if you go into LabVIEW when you're doing the second part of the lab with the clamped cantilever beam, you need to make sure that you're acquiring the right signal. So every other lab we've used IEPE in a voltage input. This one is just a raw voltage reading because the dual mode amplifier is not converting it or conditioning the signal to convert it to acceleration and digitizing it, but it's actually just reading a straight voltage input that you're going to have to make sure is scaled properly so you can load this in and make sure and test to make sure you're getting out approximately a G. And if not, you might have to do some scaling and mess around to make sure that what you're getting out of it is what it's supposed to be giving you. So that's all. Once you have that, you should be all prepared to succeed in this lab. Thanks for watching, and I hope you have fun looking at lots of different cantilever beams.
Renegade. Oh, I think what I'm looking for is right here.